Assalamualaikum. Okay, so today, inshallah, we are going to start cover our last topic in the course, and it is about fast computation of fast Fourier transform. It is not coming right. Let me see what is happening with the camera. I hope this is right now. So it is about, we have learned a lot about the transformations. So transformations, and in transformation I have explained that one is discrete time Fourier transform, and it is x of n exponential minus x of n is summation, rather let me write the forward transformation. X exponential j omega is summation x of n and exponential minus j omega n goes from minus infinity to infinity. And we discussed that there are two problems with this transformation, that first this infinity and the other one is the omega, that we cannot compute it using a computer program. Then there is a transformation which is called Z transform. So we know this as well. It goes from minus infinity to infinity, x of n, z minus n, where z is equal to r exponential j omega. And we know even this you cannot calculate, and even we are not interested in calculating this transformation. And the reason is that first, it does not really, the transformation itself does not give us any value. And the second reason is about that we are not interested in Z transform. We are only interested in finding out where all the poles and zeros are, and we want, for a causal linear time invariant system, all the poles must be inside the unit circle. So this is the second, and then we learned about these third transformations. So this is the Z transform, this is number one, number two, and our third transformation is discrete Fourier transform. And discrete Fourier transform is the representation or a transformation which can be calculated using a computer program. So this is of interest to us, and this is like 2 pi over n k n. And this we discussed that omega is actually sampled from 0 to 2 pi. Omega is sampled in capital N interval, and k is the index for that would actually give us the value of the transformation from 0 to 2 pi. And so these are the sampled version of the discrete time Fourier transform. So we are really interested in this transformation, and we have learned about properties. Then Dr. Ali has also covered last time the use of discrete Fourier transform in solving convolution, that the convolution in time, which is this, can be if length of this is L and the length of this is M, then we know length of Y, which is N, is equal to L plus M minus 1. So you can actually use DFT to calculate this convolution, provided that once you take DFT of X, it should be an N point DFT, and then you dot multiply, and when you take FFT of H, it should also be N point. So the trick is very simple, that you need to make sure that you are calculating N point DTFT, and then you take inverse fast Fourier transform and you get the answer. So convolution, even in real systems, can be implemented using a convolution summation, and many a time this is also an effective way of finding convolution, that you H, because it is a filter that you have designed, you have to take its Fourier transform only once. So once you do this, so you have this Fourier transform, N point Fourier transform, you calculate it only once, and the data you collect N number, or actually L number of samples, so you got to zero pad it to make it equal to N, and then you take the FFT, then you do just a multiplication, sample by sample multiplication, and then you take inverse fast Fourier transform. This looks very good, but now let's see the complexity of finding convolution like this, okay, versus the convolution the way we find the convolution using convolution summation. If you look at this expression, okay, this expression, so let's dissect this expression. If you do the dissection, and you will realize that this requires, for every value of K, you require N complex multiplication. So N and K also goes from 0, 1 to N. So it means to calculate a discrete Fourier transform, you require N square multiplication, where remember N is L plus M minus 1. So for calculating DFT of this, you require N square multiplication. Calculate DFT of this requires N square multiplication. Calculate DFT of this, you require N square multiplication, and then these multiplications are also N multiplications. So you require 3N square plus N number of multiplications to perform convolution using this method, which is way too expensive, than a normal convolution summation. So it does not really make sense to use this for finding the convolution. That convolution, finding convolution in time and doing it in frequency domain does not really make sense, because of this whole lot of amount of computation which you have to perform. So it's really not of any interest to us, at least for finding the convolution. The second problem that people have been trying to solve using DFT, because DFT has many applications. So one application of DFT is in radar signal processing, okay, and because you know the radar signal processing has been happening since World War II, radar signal processing. So what a radar does is that it basically transmit a high powered cosine for some time, and then it is silent listening, and then it performs another transmission, then it is listening, okay. So this is what a radar does. So a radar is, you must have seen radar just moving, and it is transmitting, and it will in one rotation. So it is rotating like this. Radar, you must have seen a radar rotating, and every time it throws a powerful signal in the air, and that powerful signal is a very high powered cosine. So it's a cosine, which is what, and then it is silent, then it's a cosine, okay. And if there is an aircraft here, So Abhinandan aircraft. So what will happen that a very little signal will come back, which will have a Doppler shift in it. So if you are sending a signal which is modulated by the square pulse, a cosine of 2 pi f naught t, and must have some phase in it depending upon the time. Okay, so this is the radar signal which is being transmitted, and once it hits this aircraft and comes back, definitely it is going to take some time for the signal to come back. It'll be very weak signal. Okay, very weak signal. So it will have some attenuation, it will have some delay of going and coming back, it will have a Doppler shift, f naught plus ft, and t minus td, this is the delay, plus a change in phase, t minus td, and whole lot of noise. So this is usually a received signal will look like. Okay, so almost the same cosine, but it has now a Doppler shift in it, a delayed in time. Its phase will also change because of this delay. You don't know that what part of the cosine will fall once you receive, and then a noise. So DFT is also very powerful in finding this cosine. Okay, very powerful, because there may be hills somewhere. So once the wave will also, this radar signal will also struck a structure like buildings and hills, but there will be no Doppler shift. So this is a clutter. So you will easily able to figure out once you take FFT that if you have a high return from a hill which does not have any Doppler, it means it is coming from a static target. And on the other hand, if it is coming from an aircraft which is flying towards you or away from you, it will have a Doppler, and Doppler will help you to find out its velocity and the time you receive a signal. So this delay will help you in finding out how far the aircraft is. So the TD will help you to find out how far the aircraft is, which is the range, and its velocity by FD, because FD has a relationship with velocity, but FFT is very important here as well. So, but again, it's computationally very intensive to compute FFT. Interestingly, in 1969, top of the line IBM computer will take 30 minutes to compute 1K point FFT. So you can just imagine that how complex, I think it is 8K point FFT. So 30 minutes, if you are finding an answer that there is an aircraft or not after 13 minutes, it is almost useless. Okay, so this was the complexity of a DFT algorithm. So usually all the radars in 1965, 66, they all were analog radars. So they'll use some analog signal processing techniques to figure out if there is a Doppler or not, and that would actually help them to find out if there's an aircraft or not. But then two scientists named Cooley and Tukey. So these are the most famous names in digital signal processing, Cooley and Tukey, because they brought signal processing in real life. It used to be just theoretical studies of signals once you discretize them. So it was basically this algorithm which they invented, and which could solve the same DFT in few seconds. This is amazing. Like an algorithm which is taking 30 minutes on top of the line IBM computer, using a simple algorithm which they devised, now would only take few seconds. So they brought signal processing in real life. Now people thought that yes, now it can be used. Now the computer's program can do real-time signal processing. Okay, so this algorithm, which is called Cooley-Tukey algorithm, and they named it fast Fourier transform. And since then, fast Fourier transform, the terminology is used that any algorithm which you devise, which can compute the DFT summation, okay, which can optimize or which can have an effective way of calculating this summation, okay, is called fast Fourier transform, FFT. Okay, and it is because of the FFT, what you say, your Wi-Fi or even 5G communication, OFDM, because the FFT is used in OFDM. So usually people would now implement fast Fourier transform in hardware, and in the next course, once you study digital system design, you will learn about the architecture which can compute fast Fourier transform, because now we are talking about supporting data rate up to 5 gigabit per second. Just imagine 5 gigabit means 5 into 10 raised to the power 9. Okay, and at this rate, processing something at this rate is just amazing, and this is only possible because of this Cooley-Tukey algorithm, which is FFT. And obviously that now you can use hardware, a dedicated hardware to implement algorithm. So this is, the excitement of learning about fast Fourier transform, that what magic they played, these two scientists, Cooley and Tukey, way back in 1969. Okay, so way back in 1969. What magic? I think 65. Sorry, it was 1965. So they played this magic in 1960. I will show you the original paper as well. So I've downloaded the original paper and I'll show you the original paper. But it's very simple. Like any sane mind would think, if you spend time, would think on the same lines. But they were like, they did it first time, so their name will live forever in signal processing books and literature. So now look, this is the formula, and you will be amazed to see how simple this Cooley-Tukey algorithm is. N is equal to 0, n minus 1, x of n exponential minus j 2 by n k n. So this is the formula for a discrete Fourier transform. So n complex multiplication for one value of k. So you have n square multiplication for, just give me a minute please. Okay. So this is, so we really looking at this, what magic can you play to reduce the amount of computation from n square to something very, 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 very small. Right on the onset, you really don't find anything which you can, because the summation, the data is changing all the time. So what can you do to reduce this? So let's see what they did. So they did what we call divide and conquer. They said, why not to split this summation into two parts? This summation into two parts, okay? Two parts. One is we do for the even indices, and the other we do for the odd indices of n. Like n, we do this summation for 0, 2, 4, 6. Obviously, you're not going to gain anything if you're doing it, but we'll shortly see that what we gain. 1, 3, 5, 7. Okay. So if you have data, so you split it into two parts. One sample you keep, the other you give it here. One sample, the other you give it here. One sample, you give the other here. So you split these samples into two parts. One part is, so now you will be left with n by 2 points. And you will be left with n by 2 points, obviously. And so you have n by 2 points, you do the summation, do the multiplications, n by 2 points, do the summation, you do the multiplication, and then add. And still, because you are doing n by 2 complex multiplication here, n by 2 complex multiplication here, so total multiplications are still come out to be n. So, right, we don't see that you gain anything here, because still you are doing n complex multiplication for one value of k. So, but let's see that what they did. So, now we need to write this, where we are calculating this for x0, x2, x4, and this summation for x1, x3, x7 like this. So we need to find out that what this how you mathematically write this. So they mathematically wrote this summation for even indices as r goes from 0 to n by 2 minus 1 x of 2r exponential minus j 2 pi, so k is replaced by 2r divided by n into n. So this is how, because once you put r is equal to 0 you get 0, once you put r is equal to 1 you get 2, once you put r is equal to 2 you get 4, so you generate these indices. Okay, so k here, the k here is replaced by 2r, so this part would actually do this part of the divide, this part of the divide. Okay, and then this part of the divide, they have summation r still goes from n by 2 minus 1, but now this time they have x 2r plus 1 exponential minus j 2 pi over n into 2r plus 1 into n. Okay, so this is the other part of the divide, which is this. The other part of the divide. So they would also write, we know, exponential minus j 2 pi n as w n. Just remember this. Okay, so so you can replace this whole part as wn, so you will write 2rn, and I'll be using it in a while. But this is very simple. Obviously, once you put r is equal to 0, you get x of 1. Once you put r is equal to 1, you get x of 3. R is equal to 2, you get x of 5. So it seems very logical and simple to understand that a summation which runs from 0 to n minus 1 is split into two halves. One half is calculating the summation for even indices, the other half is calculating the summation for odd indices, and then you have mathematically written it like this. Okay, so now what I can do is I can play a little trick, and this 2 I can take it from here and put it as n divided by 2. Obviously it will not change anything, it will again go up. So I take this 2r and bring this here. Okay, I want to do the same here, but for that I need to open this up, because you can see that it is now in a bracket. So I take, and this is all they did, they played with this exponential, and they said this exponential is exponential minus j 2 pi n into 2r into exponential minus j 2 pi, definitely there is an n, 2 pi over n into n. So they split this into two parts. Okay, because this summation is independent of r, they can bring it outside the summation. Okay, so now they have, and almost done with the trick. R goes from 0 n by 2 minus 1 x to r, and I can write this as w r n in r, short term time notation, plus I bring this part outside, so this part is w n n, this part, and this part I play the same here, that I have x x 2r plus 1 w r n n over 2, sorry, here is n over 2. So this is what they did. That's this too. They also brought it from here to here, and this they okay. So, and the trick is over, almost over, that they have split actually a, an n point DFT into two n by 2 point DFT. So if you look at this formula carefully, it is a formula for n by 2 point DFT. So they have now an n by 2 point DFT, and we'll shortly see what gain do they get. And this is again an n by 2 point DFT, but there is this vector which basically you, while combining the two n by 2 point DFTs, you got to multiply this with this factor, which in FFT is known as twiddle factor. WI twiddle factor. Okay, it's a very famous name for this factor, which is called a twiddle factor. So this part of the DFT, let's call this G of K, which is n by 2 point DFT, and this part of the DFT is H of K is X of K. So they got this relationship. Still we don't see any saving. Okay, now let's try to expand this and find out how do we get the savings. Okay, how do we get the savings? Okay, so you find x of 0 by calculating G of 0 and okay, sorry, this is not n, this is k. I have, this is because n is replaced by 2r, so I just did a little, let me do this little correction here. This is k because it is n which is replaced by 2r and 2r plus 1. Okay, so this is k, here is k. I just did a little. So now it is okay because n goes away. N is the variable of summation. So this is also r goes from 0 to n by 2 minus 1. Okay. So this is, so now we have Wn 0 h of 0. Then we have x of 1, which is equal to, you get G1 plus Wn 1 plus h of 1. Let's assume n is equal to 8. Okay, 8. N is equal to 8. Let's do this for n is equal to 8. So we can actually put 8 here, 8 here. Then we have x of 2. X of 2 is G of 2 plus W2 8 h of 2. X of 3 is equal to G of 3 plus W8 of 3. Okay, so these are the 4 point, because 8 n by 2, 4 point and 4 point DFT of even indices. For example, let me take an example. Let's say I have a signal which is 1, -1, 2, 3, 5, 0, 9. Okay, 1, 2, 3, 4, 5, 6, 7, and 8, let's say -2. This is an example which will help you to understand the algorithm. And we want to calculate its DFT. One method is that you simply write this summation. Okay. N goes from 0 to 7, x of n, and exponential minus j 2 pi by 8 n k. Okay, so put k is equal to 0, solve this summation. Then put k is equal to 1, solve this summation. For every time you have to use all these 8 values. So this is a very simple algorithm that just a loop where you're multiplying this sample with one exponential, then this sample with another exponential, with this sample and exponential, this, and then adding up together. For value of k is equal to 0, you get 1. And then you repeat it for 1 and 2 and 3 and 4 and 5. The Cooley-Tukey said, let's split it into two parts. Let's split this signal into two parts. This is index 0, index 1, index 2, index 3, index 4, index 5, index 6, index 7. Keep index 0 sample here 1 and odd index sample here -1. Then index sample 2 here, and then index sample 3 here. Then index sample 5 here, then index sample this here, then 9 and then -2. Okay, it's very simple. So you split this into two parts, the signal into two parts. First here, the second sample you give it to this part. First here, then here, then here, then here, and here. So split it into two parts. Now instead of using this summation for these 4 signals, okay, let's say we are calling this as, I can call this as G of n. Let me call this as H of n. Okay. Now for G of n, you calculate a 4 point. N goes from 0 to 3. G of n, because there are only 4 points. Exponential minus j 2 pi over 4 n k. So we calculate a 4 point and call this G of k. So this is the 4 point DFT of G of n. And then you calculate a 4 point DFT of H of n, and that is H of k. So simple. 0 to 3 H of n exponential minus j 2 pi by 4 n k. So this is the 4 point DFT of this for these points. Okay. So then what you do is take G0 from here and H0 from here. Multiply this with this and put it here. And then you take G1 from here and H1 from here. G2, G3. Now comes the saving. Once you calculate x of 4,